There you go. See, was that some time?
Let's do this thing.
Okay, let's do this. All right, high third block, high fourth block from first block. Yes, we're awake, we're functional.
First block is better. We have the camera.
Oh, God.
Okay, all right, so let's start with the inclined plane lab, okay? So the first one is static friction, and that was simple. All you have to do is take the tangent of the angle, boom, you're off to the races. Now, the second one's going to be a little bit more complex. So, speaking of inclined plane problems, in the test tomorrow, I promise you, you're going to have an inclined plane problem. So, what are the three forces that are always present on any inclined plane, no matter what?
Force parallel.
Parallel is always going to act which way?
Downhill.
Now, at this point, you need to make a decision, and I can't make this decision for you. You decide to make it positive or negative, I don't care, but you need to make a decision. Then you're also going to have force normal, which is going to be in right angles to the surface, and then you got gravity pulling straight down, okay? In terms of anything causing motion, this is the only one that could potentially cause any motion at all. The normal force is there, and that's just keeping this thing from falling straight down. Gravity is attracting it towards the center of the earth. But as far as the one that is capable of producing any motion at all, that's going to be the force parallel. Now,
good morning, Mays High School students and staff. Happy Tuesday, October 9th. Come and join the Mays High Sewing Club during Encore today in Mrs. Mann's room, H8. The doors are open to everyone, and there are no skills needed. We'll be hand sewing stuffed animals to be donated to Operation Christmas Child and socializing. Can't wait to see you there. Don't forget that tomorrow is Hat Day, everyone. Just a $1 donation to wear a hat and help raise money for the Julian Chamasko's medical expenses. Over the next month, bring personal care items, toys, stuffed animals, and other school supplies to be donated to Operation Christmas Child, an organization that assists children in third world countries. Drop donations off in Mrs. Mann's room.
what are the two possibilities of any force problem?
The class that is in the lead for the Cody is the senior class with 209 points. All seniors are invited to the Commons on Friday during Encore to enjoy an ice cream social.
At the end of any problem, either net force.
Veteran NHS members, there will be a meeting today during Encore in the lecture hall. This does not include those members that applied. Don't forget to come to the library to vote for the pumpkin contest. Voting is during passing periods or before or after school. Students, please don't forget to turn in your books. Please check your school email for overdue books. This includes novels you have used for classes, textbooks you are done with, or any other books you may have checked out for leisure that are overdue. We are also happy to renew books if it's overdue and you are still using them. Attention safe SAD members, there's a meeting this Thursday during Encore in E13. And Yoga Club is back. And all who are interested in joining should meet in Ms. Slater's room, F38, today, Tuesday, October 9th. Your pun for the day. What kind of dog doesn't bark? A hush puppy. At this time, I invite you to stand and join me in the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Okay, now,
Wet Tuesday.
the beauty of this is that you can set up every problem like this. I don't care if it's on a horizontal surface, I don't care if it's a rocket problem, I don't care. You can literally overlay this matrix onto any problem that you have. Because here's the deal, if it's a rocket, what's your force parallel?
0.
Yeah, there just isn't any, it's a rocket, okay? Even if I'm pushing something across the table, hey, there's just no force parallel. there's always usually, it's a rocket problem, you're always going to have an applied force and you're going to have an opposing force. So on any problem, if you want to start with this matrix and go, oh, okay, hey, what do I have going on? Because literally one of the most vital things that you have to do is identify what forces are in play. So if I've just got this block and I let go of it, what's the only force that's going to cause any motion?
Gravity.
Well, what component of gravity? Your force parallel. That's the only thing that's going to make this block move. That's it. There is nothing else in town. We're not pushing it. We're not pulling it. There's no strings attached. There's no rockets. There's no squirrels. Nothing. Okay? This is the only thing that's available. Now, look at what you all did. You all had your inclined plane, and here was your block, and you pushed this thing up at a constant velocity. So nugget, as soon as you see the words constant velocity, what does everything add up to?
Zero.
Beautiful. So, what is it? For force dab?
I didn't think
Okay. So, in this situation, what's the direction of your applied force? Up. You pulled it up. Don't make this difficult, right? Now, what else was there? You had the force parallel, you had your applied force, there was something else acting down the hill.
Friction.
Friction, okay? Now, here's the first thing that I'm going to look at. Here's the first thing I'm going to look at. Is when I look at your applied force on this vector diagram, and this is what your vector diagram is going to look like for that second part. Okay, this is what it's going to look like. Your applied force going up, your force parallel going down, your force friction going down, FG force normal. What I'm going to look for is that is this applied force here equal to the sum of these two forces here? Okay? That's the first thing I'm going to look for. So if this applied force is, say, 2.5 newtons, these two forces here added together should add up to like -2.5, depending on how you set up your system. Whether you made uphill positive, downhill negative, doesn't make any difference. That should be the first thing that's the first thing I'm going to look at. So I should see a scale. This angle should be drawn you should measure out an exact 30-degree angle and set that up. Okay, this isn't just some random thing. This has to be drawn at exactly 30 degrees. Here's your block, your force applied, your force parallel, your force friction, boom, here we go. Now, when you get to the next set of questions down below, where it's got on problem, let me give you a hint. Okay, what's the value of the acceleration without friction? Okay, on that one, here's the deal. If there's no friction, what's the only force available to accelerate the system? If there's no friction, what's the only?
Parallel.
Yeah. So your net force becomes your force parallel because there's nothing else going on. So on questions 1, 2, and 3, question number 1, if that goes well, that answer should be around the legal drinking age. Okay? Now, here's the deal on question number 2. Question number 2 works the exact same way as question number 1. Literally, it works the exact same way. You find your force parallel, you find your force friction, you add those together. That sum on number 2 of your force parallel and your force friction should be around 4 newtons. Okay? That's an ish, but it should be around 4 newtons. So what that means on problem number 2, here's this inclined plane. It takes about 4 newtons of force to pull this thing up the inclined plane. So option number 1, I just take my hand and I pull it up with a force of 4 newtons. That's one option. The other option is that, wow, I'm going to let gravity do the work. That's kind of a cool thing that we have living on this rock. So I need to generate 4 newtons of force. So then it becomes the challenge, well, how do I generate 4 newtons of force? Well, just like this, what if you needed 9.8 newtons of force? How much mass would you hang from the end of the string? Riley, if I needed 9.8 newtons of force, what mass would I hang from the end of the string?
A kilogram?
Yeah, because 1 kilogram times 9.8 meters per second squared gives me 9.8 newtons. So I need about 4 newtons, so I'm going to have a little bit less than like a half of a kilogram. Okay? Take 4, divide it by 9.8 meters per second squared, boom, there's your mass. So your answer to number 2 should be around 0.4. Okay, that's an ish, but it should be around 0.4. Now, here's the deal on number 3. On number 3, we use the exact same block. Okay, everything is the same. But what's the difference between number 2 and number 3? Hannah, what's the difference between number 2 and number 3 in terms of friction?
This one's going down the incline plane.
So number 3 is going down the inclined plane, so which direction does friction act? Up the inclined plane. So your answer to number 3 should be around 0.15. Okay? That's an ish, but it should be around 0.15. Cool with that one? We're good. Now, let's talk about the lab with the magnet. So here was the basic idea. You set this thing up on an inclined plane, and we're going to assume that this thing was initially frictionless. We let it go down, boom, we're off to the races. So what you're going to calculate is a theoretical acceleration. Your theoretical acceleration comes from taking your net force and dividing it by the mass to get your acceleration. Okay? Now, depending upon the angle, that theoretical acceleration is probably going to be around negative 0.3 meters per second squared. Okay? Somewhere around negative 0.3, depending upon your angle and some other stuff, but it's going to be a pretty small number. Because when you let go of that thing and there's nothing else acting on it, the only force available is force parallel. Basically, you're going to find your force parallel, divide it by the mass, boom, there's your theoretical acceleration. That's all you have to do. Then you're actually going to calculate the experimental acceleration. That one, I would recommend that you get a pen that writes, and you use distance equals 1/2 at squared plus v naught time. If you're clever, and you all are, what did you let the initial velocity be?
0.
0. Then, you know the distance, you know how far it rolled, which is 0.4 meters. You know the time, and then you can calculate that acceleration. Okay? Now, unfortunately, out of this just probably going to get you just a positive number, depending on how you measure things. But remember, that acceleration is going down the hill, make that a negative value. Then we put in a magnet. Now, I promise you, on the test tomorrow, you're going to have a question relating to this lab. I promise you, it is going to happen. Okay? You mark my words. If you get done with the test and you haven't come across a question that involves this magnet, something has gone wrong. Okay? I promise you it's going to be there. Now, the cool thing about this magnet is that the magnet always creates a braking force. Okay? The magnet never makes this thing go faster. The magnet always creates a braking force. So when you were letting this thing roll down the hill, here was your force parallel. That was acting down the hill. So what was the direction from the magnet? Grimes.
Uphill.
Uphill. So I had one force going downhill. I had the force from the magnet going up the hill. Now, here's what I want you to look at. Which force had to be bigger? The force parallel or the force from the magnet?
Force parallel.
How do you know?
Because it's going down.
Yeah, when you let go of it, it still rolled down the hill. Okay? So you know your force parallel has to be bigger than your opposing force. Now, what happened to your times when you put that magnet in there? The times get bigger and the times get smaller. Huh? Hopefully they got bigger. If they didn't, something went wrong. Okay? Something went wrong. So at that point, again, you can calculate your acceleration. So over on number 5, on the second page, where it says calculate the acceleration using displacement and time, you're going to use this equation. Okay? You're going to use this equation. You know the distance, you know the time, you need to calculate that acceleration. That acceleration on number 5, hopefully, is bigger than your acceleration that you had at the beginning. Okay? So then, what you're going to do is you're going to calculate the net force on number 7. So here's the deal. You've got your force parallel, okay? You're going to have the net force, which is what you're gonna have by taking your acceleration and multiplying that by the mass, then you're gonna find your opposing force. So basically, if nothing else, set up a chart and go, okay, I got some force parallel going, I got some force from the magnet going, and I've got a net force going. Now, here's what's vital. Out of all of these, what?
You said number 5 should have a bigger acceleration.
No, excuse me, a smaller acceleration. My bad.
Just checking.
Yeah, smaller acceleration. My bad. So, here's the deal. Remember, your net force, and only your net force, is equal to mass times acceleration. That is the only thing that ever equals net force, is mass times acceleration. So, at this point, you're going to know this number, and it should be a negative value, because your net force is pointing down the hill. You've got your force parallel, which you calculated up above. What you're going to solve for is this number. So this is going to become your unknown. So this is going to be your mass times your actual acceleration. This is going to be your force parallel that you had up above, that you already found on the other side. And this is going to be your missing number. Okay? This is going to be your missing number. So you're going to draw a vector diagram for this one. This is what I would recommend. That diagram, when you get done with it, is going to look like this. Here's your cart. Okay, you can just put it as a dot. So you can have FG and force normal. Okay? These are going to be big numbers. Okay? You might let that, like 2 centimeters equal a Newton or something like that. Okay? Because those are going to be big numbers, or maybe 1 centimeter equal a Newton. Then you're going to have your force parallel, right? And that's going to be a pretty small number because it's such a flat sign. And then you're going to have your force from the magnet, which is your opposing force pointing up the hill. So for this scale here, because they're such small numbers, I would maybe let 2 centimeters equal a Newton, or 3 centimeters equal a Newton, something like that, because it's such a small set of values. But what I want to see at some point is you show me, hey, along the motion, here's the scale that I've got. Vertically, for force weight and force normal, here's the scale that I've got. So make sure that you label those vectors, draw them on another sheet of paper, make sure that I see what the scale is here versus what the scale is there. Good with that? So typically, that opposing force usually is around 0.1 newtons. It's pretty small. Okay? That's kind of an ish depending upon your data, but typically that opposing force is a pretty small number. Anything else with that? Going once, going twice, sold. Okay. So let me go over some stuff that I promise you is going to be on the test tomorrow. I'll even tell you where the problem is going to be. On the test tomorrow, bottom of the page, 1, you're going to have a situation with a rocket. And I'm going to tell you that the force from the engines is maybe, I don't know, 200 newtons. And then I'm going to tell you that the mass of the rocket is 10 kilograms. And I'm going to ask you to calculate the acceleration. So what are you going to do wrong? Not to be pessimistic, but I've done this long enough. What are you going to do wrong?
Like 200 bucks.
You're going to take 200 newtons, you're going to divide it by 10, and you go, oh, cool, the acceleration is 20 meters per second squared, and you're done and you're moving on. Okay? Why is that going to be an absolute train wreck?
Gravity mafia.
Yeah, you never paid the gravity mafia. Okay? Next point, the gravity mafia is going to come after you with a baseball bat. Bad things are going to happen. Because the gravity mafia wants their money. So, you make a sketch. Oh, hey, I got a 200 newton force acting up. If I've got a 10 kilogram mass, Riley, what's the force acting on a 10 kilogram mass between this rocket and Mother Earth?
Do what?
What's the attraction between this 10 kilogram rocket and Mother Earth? How can you find the value of that attractive force?
The mass times the gravity, the acceleration due to gravity.
And so 10 times 9.8 is?
98.8.
Yeah. So I got a negative 98 Newton force acting down. So how much, I got $200, I gotta spend $98 on it to get off the ground. What's left over? 102. Take 102, divide that by the mass, bring it off to the races. Okay? This is going to be at the bottom of the front page. This is where this problem is going to be. You mark my words. Now, what's the only time you don't have to pay the gravity mafia? Well, when it's horizontal, but also in terms of a rocket. If I tell you you're in deep, deep, deep space, and only if you're in deep, deep, deep space, you do not have to worry about paying the gravity mafia. Now, there's also going to be an elevator problem, okay? I'm going to say, hey, I want this elevator to accelerate upward at 1.2 meters per second squared, whatever it is. And I'm going to tell you the mass of the elevator is 1,000 kilograms. Now, think this through, okay? I want this elevator to accelerate upward at 1.2 meters per second squared. If I take 1,000 and multiply that by 1.2, is that my answer? No. Why? Yeah, because what else do you have to overcome? Yeah, the weight of this thing, okay? If you take 1,000 and multiply it by 1.2, what's the only thing you're finding? If you take 1,000 kilograms and multiply it by the acceleration, which force are you finding? That's all I'm finding is my net force, okay? So I need to do that, right? But here's the deal, and I cannot emphasize this enough. Set up a chart, okay? Oh, you can go, all right, hey, I got some gravity going down. I got some tension going up. So right away, think about this. This thing is going to accelerate upward. Which of those forces is going to get bigger, gravity or the upward tension? Yeah, the upward tension, because guess what? If it isn't, the elevator isn't going to accelerate upward. So when I take mass times acceleration, and I get 1,200 newtons, that's my finette. Applied, opposing. Do you see a common theme? Every one of these is going to involve a net force, some force acting in one direction, some force acting in the other direction. Okay? I promise you, that's what's going to happen. Go back to the rocket. I fire the rocket engines, and then I shut off the engine. Okay? After I shut off the engine, what's the only force left acting on the rocket? Gravity. Guess what? It's going to create an acceleration of negative 9.8 meters per second squared, because that's the net force. Okay? Got it? Good? Okay. Now, unplug that camera, bring it back.
I hit the button.
So,
I started it again. It's okay.
Yeah. Come on. Bring the camera.
I got it.
Where should I set it?
Just hold it. You're fine.
Okay. Okay.
Huh?
Just stay right.
Great. Thanks. Okay. Hold it up. Where's it still going?
We're going. We're good.
We're good? Okay. So, here's my question. I've got a 500-gram mass on this side of the string, and I've got a 500-gram mass on that side of the string. And in here, I've got a 10-Newton scale. Okay? So I've got 500 grams on this side, 500 grams on this side, and a 10-Newton scale in between. Here's the question. What's the reading on the 10-Newton scale?
0.
0? Why 0?
Because I'm just guessing.
Well, why 0?
Why not?
You had to have something that said 0. Or was that just the first thing that popped into your mind?
I mean, I don't know. It's 500 going down one side, 500 going down the other side. Should kind of cancel out.
Okay, so the reading on the scale would be 0.
Should be. Yeah.
I think it's not.
I think that it is.
Okay? Who else thought it was 0? Chase?
No.
Why?
If it's the same force gravity on both sides, then it should be 0.
Okay. So, how many are on the 0 train? Okay? Is there another train? Riley, you said you weren't on the zero train.
The only reason I say that is because it looks like the thing's pulled out a ways.
So you're cheating.
Well, yeah,
No, you're just making an observation,
yeah,
okay?
qualitative. Yeah.
Qualitative, okay? So what's another option that it could be reading?
4.9,
Why 4.9?
because it's half a kilogram.
So half a kilogram mass weighs 4.9 newtons, right? Okay? So 4.9 is an option. Now, what if we double 4.9?
9.8.
You get 9.8. So is the spring being pulled on both sides at 4.9 newtons?
Yeah.
So could you make the argument that it could be 9.8 newtons?
You could.
You could?
Sorry. Not buying it.
Not buying it.
Nope.
Grimes? What train are you on?
0.
You're on the zero train.
Best
Okay.
train.
Now, riddle me this. What's the net force on the system? How do you know?
Constant velocity.
It's constant velocity of 0, right? Nothing's accelerating. True? Everybody cool with this? Nothing's accelerating. Could I have this situation if I had a 1 kilogram mass on one side and a half a kilogram mass on the other?
No,
What would happen?
it would go down.
It'd be accelerated because it'd have an imbalanced force, right?
Yes.
Okay. So we know the net force, we know at this point the net force is 0. Okay. So y'all are solid on the zero train. Now, let me ask you this. Let me ask you this. What if I change the situation and I just had Itty holding one end of this scale and she was just holding it. She was just holding it. And I attached a string and I put a 500 gram mass on the end. What would the reading on the scale be? 0? There'd be no tension on the string.
I didn't say that.
Somebody did.
4.9.
What would the reading on the scale be?
9.
4.9. Why?
There's 500 grams.
There's 500 grams, right? So if she was just holding one end of it, the reading on the scale would be 4.9 newtons. Okay? So anybody want to change their vote off of the zero train?
Yes.
Yeah, no.
What's the reading on the scale?
0.
No, it's not. Reading on the scale is 4.9 newtons.
Good thing I changed, huh?
Yeah. Yeah, because look. So if I take this string completely off, right, and I just hold it, what's the reading on the scale? 4.9 newtons. So all the other side is doing is acting like a wall. Okay? That's basically doing nothing but holding that in place. So this is going to end up being 4.9 newtons because of the fact that, yeah, this is pulling at 4.9 newtons, but it's like a tug of war. Both sides are pulling at 4.9 newtons, but this is just acting to hold it in place, so that's why the reading on the scale is just 4.9 newtons.
Oh, okay.
You good?
Yeah.
Okay, sure.
Yeah, he's just asking me what mass is on both sides.
Yeah, 500 grams.
I couldn't see.
Yeah, okay, got it? Okay, all right. So, let's go over here.
I think that's wrong. Delete that footage. Destroy that.
You want video when you're on.
I didn't know I'd have to hold it also. Oh my. Chase, here you go. Chase.
No. Go over there.
The one that I wrote is not here. This
We're good. Okay, so this is the type of problem you're going to see on the test tomorrow. Okay, I promise you. So let's kind of look at the situation. Let's kind of take the magnet out of this for now. Okay, we'll worry about the magnet later. So on the end of the string, I've got a 20 gram mass, and I've got this thing set up on an inclined plane. So when I let go of it, what happens? Accelerates. So the first thing that you've got to be able to do is identify the forces that are acting on the system, right? So when I let go of it, what's one force that's acting on the system?
Force parallel.
Well, acting which way?
Down,
Down, because force parallel always acts
down.
down. So I got a force parallel dragging it this way. Back up. What's another force that's acting on the system? The weight. So I've got a 20-gram mass, right? So when I let go of it, what's pulling down on the 20-gram mass? Give you a hint. Rhymes with gravity.
Gravity.
Tragedy.
Tragedy. As could be. Okay. So if I'm just holding it, and I got a 20-gram mass, if you do the math, 20 grams is 0.02 kilograms. Multiply that by 9.8, you get 0.196 newtons. Okay? So this is being pulled down with a force of 0.196 newtons. So when I let go of it, what do you know about your force parallel? If this is 0.196 newtons, is my force parallel bigger or smaller than 0.196 newtons?
Bigger.
Bigger, right? How do you know?
Because it goes down.
Yeah. Now, when I let go of it, is there a net force?
Yes.
Yeah.
Sure.
How do you know? Terracotta. How do I know that there's a net force? No. Nope. Not because it's moving.
Because it's not at a constant velocity.
It's accelerating, right? Okay? So as soon as you see acceleration, what do you know is not zero? Net force. Okay. So here's the deal. So I let go of this thing, right? And I begin to see an acceleration. So if you look at this in terms of what you've got, I've got force parallel dragging it this way. What's the direction from the suspended mass? Which direction is that force acting? Up, right? It's pulling, this is, because if this is trying to pull it this way, so it's like a tug of war. This is trying to pull it this way, force parallel is trying to drag it down this way. Which one's bigger? Force parallel, right? Now, here's the deal. So, when I have this set up, and let's say I get my net force and I want to calculate the acceleration. At the end of the day, how do you always calculate your acceleration when you have your net force? What do you divide by?
Total mass.
Which mass?
Total.
It's going to be this mass plus the 20 grams, because that net force isn't just accelerating this cart, it's also dragging that 20-gram mass with it. Now, what if I did this? I'm going to lift this up, pull that block out. Okay? Now, when I let go of it, now what does it do?
Ooh, goes the other way.
Goes the other way, right? So now, what's the direction of the net force? To the right, because that's the direction that's accelerating, right? So by removing the plank, what did I get rid of?
Force parallel.
Got rid of the force parallel. Do I still have the same applied force acting on it, trying to pull it this way?
Yeah.
Why, Chase?
Okay, you didn't change the math.
Yeah, I still got a 20-gram mass dragging it down. So if this is going to be the situation, and I promise you, you're going to have a problem like this too. I'm going to take a 20-gram mass with some mass, and I'm going to suspend it from the end of the string. It's going to drag this cart. So if there's no friction, what's the only force available to accelerate the system?
Gravity.
Acting on what?
The mass.
Which mass?
20.
The 20-gram mass. Is gravity pulling down on this?
Yes.
But
There's force normal.
balancing that out, right? So gravity is pulling this down, but the normal force is acting up. So this is not acting as an opposing force because of the fact that this is balancing out. Now, but no matter what, even without that block being there, when I calculate the acceleration, Caden, what mass do I divide by?
Total mass.
Total mass. Whether that block is there, it's always going to be divided by the total mass. Now, let's put that back in. Now, I flip it over. There you go. Okay. Now when I let go of it, now it goes down the hill. So now I have the exact same force pulling it this way, but now my force parallel is going to be bigger. Now, let's change the situation. Let's make it even more complex. So now we're going to put a magnet in there. Okay? So now, watch what's going to happen. Make sure that goes through. Okay. So watch what happens. Watch what happens to the motion of this thing until it hits the magnet. and then watch what happens after it clears the magnet. So we're here. So, what happened before it hit the magnet? Sped up. Why?
Because force parallel is bigger than this.
Okay, so force parallel was bigger than your opposing force. Now, as soon as you hit the magnet, what did it begin to do? So, think about this. What's the direction from the magnet? Caden.
Up.
Okay, so here's the deal. Is the force parallel still acting down? But what's the direction from the magnet? Up. What's the direction from the string? So I've got two forces acting and only one force acting down, right? So I got this. Remember, the force of the magnet always acts up the hill. Now, as soon as it, hold on. Bird. Back off me. Okay. As soon as it clears the magnet, what does it begin to do? Speed up again. Why? What did you lose once it clears the magnet?
That force.
Yeah, so then you're back to having your force parallel being bigger than this. Now, what if I do this? If I give this thing, hold on. Okay, I give this thing a push, right? Now, going in, as soon as it hits the magnet, what does it begin to do?
Slow down.
So now, going in, okay, when I gave it a push, what's the direction? Cart's going this way. What's the direction from the magnet?
Down.
Down the hill. What's the direction of my force parallel? Down the hill. What's the direction from the weight? Up the hill. So, so going into it, I have two forces trying to make it go down the hill, but only one force making it go up the hill. Now, here's the question. When it hits the magnet, does it accelerate?
Yes.
Yeah.
So what does that mean? What is your net force not equal?
Zero.
Zero. So that means something had to be making this thing slow down. Now, when I let go of it again, though, it begins to accelerate. Now, at this point, if you notice, it's pretty much moving at a constant velocity. So this is why I set this particular angle. So when I let go of it, it speeds up initially, but then you pretty much have constant velocity. So when this thing is rolling with constant velocity, what's the sum of all the forces, Eddie? Zero. So think about this. So if that's the case, I've got my force parallel trying to drag it down. I've got the force, so when I let go of it, what's the direction of the force from the magnet? Up. This is going up. So I've got two forces going up and only one force acting, and they would all add up to equal zero. So here's your takeaway. No matter which direction this thing is going, what's the direction from the suspended mass? Up. No matter what, this thing is always trying to drag it up. What's the direction relative to the magnet in terms of the opposing force? But it's always going to be just the opposite direction. So no matter which way this thing is going, the opposing force always, from the magnet, is always in the opposite direction of motion. So this kind of is like magnetic brake. It's like magnetic friction. So remember, friction always acts in the opposite direction. This magnetic braking always acts in the opposite direction. So it's kind of cool because there's no direct contact, but yet, ooh, it's kind of weird.
Just checking.
Doubting Thomas. Legitimate. Okay. Got this. I promise you, there's going to be a question like this on the test. Now, at the end of the day, I'm going to ask you to calculate an acceleration. At the end of the day, you're going to have a problem like this, you're going to calculate the acceleration. What do you divide by to get the acceleration? Total mass. Including the 20 grams, don't forget the 20 grams, and this whole system here. Got it? Good? Grand? Back we go. So you can stop that.